computer. All right, so that's going. All right, guys, so like we mentioned, we'll talk about the Rankine cycle today. We'll start into that's chapter 11 in the current version of the text. Be chapter, chapter 11 in the current version. That's chapter 9. I'm sorry, chapter 10 in older versions of this text. And we'll get started from there. Now I am going to, because I've got some PowerPoints we'll look at real quick. So I'm going to share screen. And we'll just quickly review kind of the basics of auto and diesel cycles. So these chapters that we're in, chapters 10 and 11 in the current edition of the text, deal with ideal cycles, idealized cycles. What we're going to look at in chapter 11 are looking at vapor cycles, whereas chapter 10, we just looked at with the auto and the diesel cycles, those are for gas cycles. So mimicking internal combustion engines where I've got just a bubble of gas, a bubble of ideal gas, a bubble of air is my working fluid. In chapter 11, it focuses on vapor cycle. I'm sorry, not vapor. Yeah, vapor cycles. Any kind of device where the working fluid can shift phases between liquid and vapor phases. So what we're going to apply it to will be like a modern version of a steam engine, which you might find in a large scale power plant, for example. But the strategy is about the same, honestly. Put together your organized, your given information. Like we saw with the auto cycle, which properties have an idea of what the properties of different states are, and have an idea of which ones are constant between the states. You have kind of a roadmap of what that looks like, then that will allow you to really kind of guide your process. When you're dealing with the gas cycles, like the auto and the diesel cycle, because those are ideal gases, your main thing is you're trying to figure out, can I get to the temperature in each state? If I can get to the temperature at each state, I can do a first law analysis in each state. In the vapor cycles in chapter 11, that's not going to be too much different. The difference is, can I get an enthalpy value for either the water or the refrigerant, whatever it is I'm working with? Can I get the enthalpy value at each state? If I can get the enthalpy value at each state, then I can figure out the first law at each state. But again, the strategy is going to be about the same. Organize your given information, figure out what properties you know, what properties you can find, and then identify all laws and relationships that you can apply between the states. Draw diagrams, look back at your diagrams, so you have an idea what each of these states are referring to. So if the problem statement says things like prior to the isentropic compression, you know what state it's referring to. So this is the auto cycle. We talked briefly last time about the diesel cycle. And we said that because the diesel cycle's got this expansion process from 2 to 3, there's this cutoff ratio that is also involved in calculations that shows up in the efficiency. And again, I'm going kind of quickly because this is a review for us. So if you compare the auto to the diesel cycle, if the compression ratio is the same, the diesel cycle will actually be less efficient. This quantity will always be greater than 1 because the cutoff ratio has a minimum value of 1. This ratio here will always have a value greater than 1. So at the same compression ratio, the same R value, if you compare an auto to a diesel cycle, the diesel cycle will always be less efficient. What we find is with modern diesel engines, we can run those at much higher compression ratios because of the characteristics of the fluid and fuel. So we can run a higher compression ratio in a diesel engine. Therefore, we tend to get a higher efficiency out of those engines. All right, so we just quickly through that because that's a review for us. Today, our focus is going to be, as we mentioned, chapter 11, it's Rankine cycles. This is the ideal cycle. It's going to closely mimic any type of situation or cycle where you got a phase change. So refrigeration cycles, heat engines are normally where we're going to apply these. Similar to the things that we looked at in chapter 6. Right? And so basically in chapter 6, we talked about the Carnot cycle. And if you look in chapter 11, they mentioned at the very beginning of that chapter, talking about the Carnot cycle and making comparisons. We're going to take this is also an ideal cycle. Rankine cycle is it's a completely reversible cycle, just like the Carnot cycle. And so therefore, the situations that are adiabatic are also going to be isentropic because they're reversible already by definition of the Rankine cycle. That's an idealization. We're going to all these processes are reversible. And so from 1 to 2, we're going to have an adiabatic compression because it's reversible and adiabatic. It's also going to be isentropic. So isentropic compression from 1 to 2. We're going to add heat at a constant pressure from 2 to 3. We're going to do an isentropic expansion. So adiabatic, and because all these are reversible, it's adiabatic and reversible from 3 to 4. So it's isentropic from 3 to 4. And then the constant pressure heat rejection. We see this graphically, again, similar to what we would have seen in chapter 6. Essentially the same model. They've changed how they draw the condenser just a little bit. And you could just as easily draw it the way we did in chapter 6, drawing a square down here in the bottom with heat going out of it. Okay? But it's the same basic process. It's just now we have some understanding about entropy at this point. But so we're going to apply the Rankine cycle to an engine just like this. And you can see they've labeled the steps here. If I go back, again, from 1 to 2 is this isentropic compression. That's essentially, in a physical sense, that's going to be an ideal pump. So a pump, its goal, the goal of that pump is simply to increase the pressure of the liquid to get high pressure liquid going into the boiler. So if I got high pressure liquid going into the boiler, we said from step 2 to 3, that's constant pressure heat addition. So I'm going to add heat to this liquid at a high pressure. And basically, I'm going to boil it off. I'm going to get it to become a high pressure vapor coming out of this boiler by adding a bunch of heat into it. So high pressure vapor going into the turbine at state 3. 3 to 4 is isentropic expansion. So isentropic expansion, we'll represent that with a turbine. So to go from 3 to 4, we're going to expand the working fluid, extract work out as we do that. So we'll have a lower pressure going out at 0.4, some probably, hopefully all the way down to like a vapor liquid mixture. There's a physical limit as to how much the turbine's going to allow us to do that without getting chewed up. But again, coming out at the very least, saturated vapor or probably some mixture coming out at 4 at a low pressure. And then again, constant pressure heat rejection. So in the condenser, low pressure mixture coming in, lose heat, cool it down, get it condensed all the way down to liquid form. So I've got low pressure liquid. Now the condenser ready to go back into the pump at state 1, process release. Okay. If we assume completely ideal Rankine cycle, assuming there's no heat transfer and it's completely reversible at any of the pressure changing devices. So pump and a turbine in the case of a heat engine, compressor, turbine and or throttling valve in the case of a refrigerator. We'll look at a problem today where we've got an isentropic efficiency, so it won't be 100% ideal, but I'll show you kind of how that works. That's a nice review of isentropic efficiency. Graphically, again, remember we're going, because we're going to be dealing with water in an engine or some sort of a refrigerant in a refrigeration cycle. So we've got to work our way around the on a TS or a PV diagram, working our way around the saturation zone. So if it's anyway, you can kind of see these are lines of constant pressure going across here, and we're going to follow a long line of constant pressure to go from 2 up to 3, right? And then we're going to follow a line along a line of constant pressure going back from 4 to 1, back right here to the point of saturated liquid. And these are, again, these are isentropic from 1 to 2, so going up in the straight up vertically on 0 change in the S axis, on the entropy axis, and 0 change from 3 to 4 in an isentropic expansion, dropping down to the lower pressure from 3 to 4 on the turbine. So again, you can see that graphically. Okay. So one thing to mention here, remember when we looked at the Otto and diesel cycles, those were just a piston of air that we were adding heat to and cooling down, allowing to expand and compress. But that was a closed system. We had just a bubble of air in a piston, no mass coming in or out. In the case of the Rankine cycle, if we look at each one of these elements here in this diagram, each one of these elements now is a control volume with mass going in, mass going out. I can look at the whole system as one big closed system. Or I can look at each one of these individual elements as its own individual system where there's mass crossing the boundary. So in a Rankine cycle, if I'm looking at each individual process, I'm looking at control volumes. So I'm gonna have H's basically. So it's in the simplest sense, with the Otto and diesel cycle, you're dealing with U values because those are closed systems. In the case of the Rankine cycle, you're dealing with control volumes. So at the very least, those flowing masses, you're going to be dealing with enthalpy, you're dealing with H values. That's one of the biggest differences, and also the fact that we use property tables instead of making ideal gas assumptions. But otherwise, they work much the same. I pulled, so I'll stop sharing at this point. I have to go to the document here. So I pulled out of the 9th edition here. I found, I think 23 is a nice problem to look at. Let's focus there. Okay. It's 23, that's not the best picture of it there, but it says a steam Rankine cycle operates between pressure limits of 1500 psi in the boiler, and I'll write the givens out on paper here in just a second. We're going to go from 1500 psi in the boiler to 2 psi vacuum in the condenser. It's less than atmospheric pressure in the condenser. The inlet temperature for the turbine is going to be 800 Fahrenheit. The turbine has an isentropic efficiency of 90%, so it's not a completely isentropic turbine. But the pump will treat the pump as isentropic. The pump losses are going to be negligible. So we'll treat the pump as ideal and isentropic. The cycle will produce 2,500 kilowatts of power. It's going to be our network out. And it's got 4 things it wants us to find: the mass flow rate, the power produced by the turbine, the rate of heat going into the boiler, and the overall thermal efficiency. So like I said, I'll write these givens out with you guys. I'm going to set myself some room here, so I can set my book next to it. So again, I'm looking at 1023 in the 9th edition. I don't think that problem exists in the 10th edition. I'll have to look, find it, let me know. This is, it doesn't, yeah, I didn't think I found it. This is 1023 in the 9th edition. So that's in the video now. You can go back and look at, if you want to kind of study from this, go back and look at that. Let's collect our givens here like normal. We've got a Rankine cycle. We have water as our working fluid, so it's a steam cycle. What do we got here? We've got, you basically have a high pressure of 1500 psi. 1500 psi. You've got a low pressure of 2 psi. Again, an atmosphere is about 15 psi, so we're running lower than atmosphere on the low side. That happens. That's kind of an ideal thing. It means we're getting as much work as we can out of the turbine there. The temperature out for the turbine. I'm going to talk about what states these are in a second. But it just simply says the temperature out of I'm sorry, that's the inlet. I apologize. The inlet temperature for the turbine is 800 degrees Fahrenheit. The turbine has an isentropic efficiency of 90%. The net power produced by the cycle, W net out, can be 2,500 kilowatts, 2.5 megawatts, 2,500 kilowatts. They want us to find mass flow rate. They specify the mass flow rate in the boiler because it's a continuous loop. That's going to be the mass flow rate in all the units. So we're just going to call it M dot. You can specify M dot boiler, but it's the same M dot for everything. They also want to know the power produced by the turbine. So I'm just going to call that the power out. I want to find the power out. They want to find the rate of heat supplied to the boiler. So we're going to say Q dot N or Q dot H if you like, if you want to use the subscripts from chapter 6. And then the thermal efficiency. Efficiency sub TH, thermal efficiency. How good is this thing at converting the heat going in into net power output? That's going to be the efficiency. Okay. Let's see. Well, they did specify M dot in the boiler. So a common place to start would be, we'd say, all right, well, let's look at the boiler. And I would always say, where do we start? That's always good problem solving. What is it we're trying to find? What is it we're looking for? So if you wanted to look at the boiler and say, well, let's look at the boiler. I mean, if it helps, I don't know, it might help to just draw the whole thing real quick. Boiler, and then we can kind of familiarize ourselves with the states. If you look at, I've got a diagram here. So the boiler, I know it's out of focus, I apologize, but you can see the boiler's coming into the boiler is state, what we call state 2, coming out of the boiler is state 3, coming out of the turbine is 4, out of the condenser's back around to 1. So 1 goes into the pump. So if we draw that here, the boiler coming into the boiler is state 2. Coming out of the boiler is state 3, that goes into the turbine. That's my power output there, and I've got heat going into the boiler. The rate of heat going into the boiler. And then from there, I go into a condenser. That's where I'm losing heat. From there, it's going to go into a pump where I'm going to put a little bit of power input. Again, coming out of the turbine is 4, coming out of the condenser, going into the pump is 1. Okay, so I've kind of drawn that quickly. It's a little sloppier than even normal because this is just simply for reference. Now I'm going to put up the top here. This is it's going to be page 1 of something. It's going to be L26. Otherwise, I'll lose track of which page I got because I'm about to have a bunch of pages here. All right. The boiler then. If we look at the boiler, because that's what the problem statement is asking for, find the mass flow rate in the boiler. So I've got state 2 coming into the boiler. I've got state 3 going out. The only other thing crossing the boundary is the rate of heat coming in. Well, didn't we have work out or work net out? So yeah, so you do know the net work out, right? That is known. But what this represents is the difference between this and this. Right? So eventually we will use this. We will end up using this eventually. You are correct. We gotta, how we get there is a few more steps. Yeah, no, absolutely. And you could start here and work your way back, and that would be perfectly fine. There's no wrong, there's so many unknowns to go after here. There's no wrong way to start with this. Yeah. I kind of, and again, the way I'm approaching it, which doesn't necessarily mean this is the right way, because the problem statement specifically said, what's the mass flow rate through the boiler? So a lot of people would look at this, say, well, let's start at the boiler, which doesn't necessarily mean that you have to start that. I'm just kind of approaching it maybe the way that most people would. Yeah. Does that help some? Okay, cool. So if we did that, right? So if we look at the first law here, that's going to be Q dot N. It's going to equal M dot times H3 minus H2. This is, I've moved mass out minus mass in over to the other side of the equation. If we're if we're being hardcore about it, like we might in chapter 5, we'd say Q dot N is equal to M dot, I'm sorry, plus M dot H2 minus H3 is equal to 0, but I've skipped a step there. So this is Q dot N is equal to the energy of the mass out minus the energy of the mass in. And we count our unknowns here. Well, I don't know Q dot N. That's one of the things that's actually asked for up above. I don't know M dot, so that's 2 unknowns. Can I find these H's? Well, let's look back. They did give us a bunch of stuff up here. This is my high side. This is the high side. The high side is going to occur in the boiler. The low side is going to occur in the condenser. So they've given me a high pressure. This is P2 and P3. Because by definition of the Rankine cycle, heat addition occurs at a constant pressure, the high side pressure. And the heat rejection is going to occur on the low side. That's P4 and P1. That's what they've given you up here. So they've given you P2 and 3, and they've given you P4 and 1. They said the temperature at the inlet of the turbine. Well, that's here. That's between the boiler and the turbine is state 3. It's here. So they've given me this temperature they've given me at the inlet of the turbine. That's actually T3. So if we look at properties here, I know both P3 and T3. That would be enough to give me H3. H3 is known. Okay. If I look at state 2, well, I know P2. But I don't know a second property. Okay. Don't know a second property yet. Okay, so I'm gonna have to come back to this one. Right now, I got one equation, 3 unknowns. All right. Now, getting to H2, and by the way, the secret to a Rankine cycle is can I get H values around the entire cycle? With an auto or diesel cycle, the secret is because it's an ideal gas, can I get temperatures all the way around the cycle? In an auto or diesel cycle, if I can get the temperatures, I can find all the other properties. In a Rankine cycle, the goal is really going to be, can I get to the enthalpy at all points in the cycle? Okay. In this case, if we look at, if we continue around, maybe we do kind of the same thing we've just done here, where I've looked at the boiler and said, well, let's look at the first law for the boiler. If I do the same thing at the other units within this thing, if I look at the turbine, so if I look at the turbine, well, coming into the turbine, I've got mass coming in at state 3, and going out of the turbine, I've got mass going out at state 4, and then I've got a power output going. So if I look at the first law here, we've got power output is going to equal the same mass flow rate. And this is going to be mass in minus mass out. So it's going to be H3 minus H4. It's technically minus the power output plus M dot H3 minus H4 is equal to 0. Simplified that. I've skipped a step there. So the power output is going to equal energy of the mass in minus energy of the mass out. We're neglecting kinetic energy because we don't have enough information to find them, and we think it's probably going to be negligible. And there's just enough other stuff going on anyway. We've already established I can find H3. Finding H4, what do I know about state 4? Well, I know P4. If I look back at my givens, I know P4, I know the exit pressure, I know the pressure all the way around the cycle. They've not given me anything else about state 4, but they have told me this. They said, hey, this turbine is not 100% efficient. It's not an ideal turbine. It's not an isentropic turbine. It's within 90% of the isentropic turbine. Okay. So they told me something else about state 4 here. They've told me the isentropic efficiency for this turbine. So what I can do is I can say, well, let's look for the actual power output, which means I would find H4 actual. They've told me the efficiency of this thing is 90% when compared to the ideal isentropic. So that efficiency ratio means this is H3 minus H4 actual divided by H3 minus H4 isotropic. I should write that on the next one. Get this slide out. L6, this is L26, L26, page 2 of something. Okay, so I'm gonna write this a little bit bigger. I know 0.9, 90% is going to equal H3 minus H4 actual divided by H3 minus H4 at the isotropic state. So what I can do here, I can say S4 isentropic is equal to S3. Meaning I'm going to need S3 up here. So given S3, that gives me my second property. And I can find H4 if this turbine is isentropic. The turbine's not isentropic, it's only 90% to isentropic. Oh, got that down here, sorry. But what I can do is I can find, well, what is H4 if it's isentropic? I've got H3. It's 90% of the way there, so that gets me to H4 actual, which would give me that solidifies that one. Okay. So I've still got, I've kind of helped myself, right? I've still got, so basically I'm working now with three equations, I guess, right? Three equations so far. I got one equation here, Q dot and M dot are not known, H2 is not known. Got an equation here, power output's not known, so I've added another unknown. But I do have a path to get to H4 actual here. So I've not really gotten rid of any unknowns yet. Added more, but I'm getting a path to my way around the cycle. Now, if I look at the pump, and this is kind of how a lot of times with the Rankine cycle you want to approach it, is just start looking at the individual elements. What can I find with the individual elements? Does that get me a clear path back to a final solution? And it's really, mathematically, it's not a lot more complex than what we've already done. It's just, now I've got 4 different states I'm processing. So I've got to kind of try to help keep them straight. So if I look at if I look at the pump, for example, because I kind of come back to, well, you know what? If I could get H2, and that eliminates, I'm going to have to find H2 to get to either Q dot N or M dot, one of the two. Okay. So if I look at the pump, well, the pump's got state 1 coming. And it's got state 2 going out. Pump. And it's got a power input going in. And the problem statement said this pump is ideal. It's an isentropic compression. So there's a neat trick we get to use for an ideal pump. They'll tell you for an ideal pump, you get to use this expression. The ideal pump doesn't increase the temperature of the fluid coming through, right? All that happens is an ideal pump, the work in ends up being, you end up generating a change in enthalpy. In this case, it's going to be H2 minus H1. If the temperature does not increase, and because it's a pump is only pushing liquid. So if I'm pushing liquid, the enthalpy change, if there's no temperature increase, just simply ends up being the specific volume times the change in pressure. This was in chapter 4, I think we talked about. Maybe chapter, I don't know, chapter 4 or 5, we talked about this briefly. And then I think I said at the time, we probably won't use this again until we talk about Rankine cycles. If we talk about Rankine cycles at the end of the semester, here we are. So you went back and looked, you would find this. Now you don't necessarily, here's what you can do is you can look at this diagram and say, well, you know what? Here's what I know is the power input, capital W, is equal to m dot H2 minus H1. Right? That's the first law analysis of this pump. Because I've got power N. So power N is going to equal the energy of the mass out minus the energy of the mass in. And all I'm doing here is I'm saying, well, little Wn, which is just the power input divided by m dot, is equal to H2 minus H1. And we say, all right, well, how do we find H's? Well, what is my substance? It's water. Well, what do we know about a pump? It's liquid. A pump is only going to push liquid water. So if it's liquid staying a liquid, I can actually approach the enthalpy difference. And this is one way I can do it. I can use this as kind of a relationship. So this becomes now the work in ends up equaling, because again, it's delta H, and I can use for a liquid, I can use B specific volume times the change in pressure to get there. Okay. And again, what does this do? This represents the change in enthalpy. Okay. Now, how does this help us? Well, if I look at properties, what the heck are we looking for? Remember, we're trying to get to m dot up here. Ultimately, I'm trying to get to, if you look all the way back up here, trying to find m dot and these two, the power output for the turbine, the heat going into the boiler, and the overall efficiency. Ultimately, these are the things I need. How do I get to those? Well, I need to be able to find the enthalpies. I need to find H2 to be able to get to one of these. Okay. And then once I know m dot, then I can get to the power, because I know I can get to both these H's here. So really, I'm kind of down to, I need m dot, I need this heat, and I need this power output. And I'm going to have to get m dot to get there, which means I'm going to need H2. How am I going to get to H2? Well, you can look down here at the pump. I know the pressures, right? I know the pressures. Can I find H1? Because if so, then I could maybe get to H2 directly. What do I know about state one? Well, I know P1. Okay. I know P1, that's given. Do I know a second property? Well, what's going on at this point? State one is coming out of the condenser. In an ideal Rankine cycle, what we're going to do coming out of the condenser is you want saturated vapor. I'm sorry, saturated liquid. So you want saturated liquid coming out of the condenser. That's your goal. So if it's an ideal Rankine cycle, and on the pump side, they said it is ideal. There's no pump loss. You actually end up with, that's an assumption you can make. That you can say that at the exit of the condenser going into the pump, it's going to be saturated liquid. So that's enough information to find H1. Given H1, and I can also go ahead and use V1 here. I can assume that the specific volume is going to be reasonably constant. Okay. So if I assume that the specific volume is reasonably constant, because it's like density of liquid water, it's not going to change much. So if that's V1, then H2 becomes my only unknown here. H2, you know, if I go back up here and say, well, remember, I didn't know a second state about H2. What do we know here? Well, it's coming out of this pump. All I know is it's a liquid that's at a jacked up pressure, but I don't know a temperature or another state. I don't have enough information to find H here, but I do have a clear path down here. This is a common thing you'll do in a Rankine cycle problem. Is at the pump, you just do this right here. Enthalpy change, unless the pump has an efficiency, the enthalpy change is going to equal this VDP. And then I just find, if I know H1, because if I know the pressure and it's saturated liquid coming in, then I find H1, and I can find H2 this way, where I say, well, H2 is just equal to the initial enthalpy coming into the pump, plus the specific volume coming into the pump, times the difference between the high and the low pressure. And that'll be enough to get me to the second enthalpy. So with the second enthalpy in hand, I can go back up to these other equations. Say, well, now I know H2, so that comes off the board. Now I need to know m dot, Qn, and that would unlock down here work out. So now I'm down to two equations with two unknowns up here. Okay. I'm sorry, 2 equations, 3 unknowns. I'm down to 2 equations, 3 unknowns up here. Okay. I know these problems are a lot. They are a lot. I get that. Okay. But if you look at it, I mean, if you look at the algebra, it's really just algebra. It really is. It's not like we're not doing differential equations here, ladies. Okay. So I've got a path to H2. I think we might be at a point where we can start plugging some numbers in, right? Let's see. Do we want to get? And let's get a clear path to M naught, and then we'll start plugging numbers in. So all that to say, now I'm down to 2 equations, 3 unknowns. I don't know M dot. I've got my enthalpies so far handled. I don't know Q dot N. I don't know the power output. And the question earlier came up and said, well, what do we do know this guy. We do know this guy. This guy's going to give me something. What does this guy give me? You got the net power output. What does this represent? Anybody tell me that? What does the net power output as a concept represent? Yeah, it's the difference between the power out and the power in. Okay. Which this occurs at the turbine. Go back to your diagram. This is M dot. We've already done this one. Okay. This is M dot H3 minus H4 actual. M dot times H3 minus H4 actual, which we've said we can get to those. And the power input, that's M dot, that's for the pump. That's going to be H2 minus H1. We just said we can get to these. And we know this value. This is 2,500 kilowatts. All the H's are known. M dot's the only unknown here. All right. M dot now becomes 2,500 kilowatts, which we'll want to convert to some kind of, we'll have to go look at what is BTUs per second, because this problem's in English. It's per kilowatts. We'll want that conversion factor. And then I'm going to factor all these H's out. So in the bottom, it's going to be H3 minus H4 actual. And then I'm going to distribute this negative sign. So it's going to be minus H2, and this H1, it already has a negative sign, so it's going to pick up another negative sign. It's going to be plus H1. So I need to know this conversion factor. Let's look here. It's sitting next to me if I can find it. Power BTUs per second. That was horsepower. That's not going to help me. No, I don't have a direct, do I? Yeesh. I can go from horsepower to watts and horsepower to BTUs per second. So let's go kilowatts to BTU per second. All right. If we trust Google, it's pretty close to 1. That's interesting. 1 kilowatt is about, well, yeah, okay, because that's right. I could do kilojoules. I could just do BTUs to kilojoules because a kilowatt is a kilojoule per second. So that could work, right? And that's what we're seeing here. Duh. I don't know why I didn't think of that. 1 BTU per second is, 0.9478. 0.9478 BTUs per second for every kilowatt. Sorry, it's a little small. 0.9478. Okay. Okay. That gives us M dot. You guys see now this whole thing falls out, right? I got a clear path to a solution. You guys want numbers? You guys good? If you guys are good, I'm good. All right, you see, at this point in the semester, you should be able to do this. If not, that means you need to know how to do property tables. I'm okay if you guys are okay, you can do property tables and get to a solution. I've got, if you trust Chegg, I don't, but you know, these are that's what Chegg gave me. You're welcome to those. Okay, let me see if I can focus that a little bit better. Nope, that's no better. I'll write them out. Again, I didn't verify these, so please understand that these are Chegg solutions, so take them for what they're worth. But I'll write them out here for you so you can see them a little bit better. This, I don't know why I can't get it to focus on these. But at any rate, MDOT is 5.437 pound mass per second. Now, I don't know if they're using the same models for their property tables that our book is using. I don't know. That's the thing about Chegg solutions. We have no idea where their values are coming from. Okay, so it's probably pretty close. But if you do it with your property tables, you're probably going to get something a little bit different. They're saying the power output for the turbine is, they're suggesting 2394 BTUs per second, which we probably would convert that to horsepower or kilowatts. They're saying QDOT coming in is 6875.6 BTUs per second. We didn't talk about efficiency yet. How do we find the thermal efficiency for any heat engine? How would you find the thermal efficiency? By definition, what is efficiency? Yeah, actual over ideal, or what you want, about what you got to do to get it. In an engine, what do you want out of the engine? Net power output. That's what you want. Net power out, which is given. What do you have to do to get it? Heat. Heat. Q.N, which we've now found. So they're saying the efficiency, based on these numbers, they're saying it's about a 34.46% efficient is the number they're getting. Well, like I said, if you guys can't find enthalpy, because the only thing really missing at this point are enthalpy values. If you guys can't find enthalpy values at this point, I don't know what to tell you. Okay, come see me. Seriously, come see me, because that's hopefully you understand that's a big deal. Okay, we good? Everybody good? I'm good. All right. You guys have a wonderful weekend. I will see you next week.